Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, ladies and gentlemen. It's my great pleasure to welcome you now to the second day of the Paris Software Summit. This introduction is very easy for me because donGÇÖt is a great colleague of mine. He is the initial... He is the founder and manager of the RISE group in Microsoft Research Redmond. So RISE stands for Research in Software Engineering. Many of the tools and technologies that you're going to see in the demo fest later this morning will be coming from his group, and I hope you're going to enjoy those. Wolfram has many accomplishments to his name. You can read about them in here, but I think it's much more important that you hear now about what he thinks of the future of software engineering. Wolfram.
Yeah. Hello, good morning. Thank you for the wonderful opportunity to tell a little bit about the work that my team is doing in Redmond. So I think the picture should show you in some sense where we are heading. We are heading in the next generation. So in some sense, we will retire at some point, and this generation will take over. So I'm happy to reflect on the future of software engineering. But whenever you think about the future, never forget the past. And so I want to tell you actually where I come from a tiny bit. And so, as you all know, software engineering started in 1968, or that was when the term was being defined at a summer school in Bavaria. And it turns out that the person who defined software engineering, who used it the first time, is actually my advisor's, my PhD advisor's advisor. So in some sense, my grandfather. So software engineering runs somehow in my blood. I didn't hear anything about software engineering until I started studying computer science. That was '83, and then we got a textbook from Ian Somerville, which is now in the 9th edition. But in one of the early editions, he defined software engineering as follows: produce high-quality software with a finite amount of resources to a predicted schedule. And I think now we have a more elaborate definition, but this one is still pretty good. And what's really interesting about it is if you step back and replace software by car, for example, or automotive, then you get a different definition. Automotive engineering, produce high-quality cars with finite amount of resources to a predicted schedule. And that's actually interesting. We are, as software engineers, not so much different than other engineers, except that other engineering disciplines exist for a long time. And so what I think we could do is actually learn a little bit from other engineering disciplines. And so that's one of the thrusts that I wanted to convey today. So I want to talk a little bit about analytics, what goes on in other engineering disciplines, and whether we can take it over for software engineering. I will talk a little bit about the hardware industry, which had actually some success in using formal methods. And what does it actually mean for the software industry? And ultimately, we have, in some sense, in such exciting times where our technology changes so quickly that I think as software engineers, we should actually see where the trend in the technology is going. And so how will future platforms and future developers look like? And where do they come from? Do they come from only industrialized countries or actually developing countries? So let's see a little bit where we are going. So these are the three thrusts that I want to talk about today. Let's start with analytics. So as you know and heard, I am still a researcher. That's where my passion is. But I'm also a manager. As a manager, you have to read lots of managerial books. And so one of the interesting ones that I came across last year was Analytics at Work. And so this is written by a professor for economics. And one of the distinguished books from the last year. And what he figures out is actually all the industry is currently transforming because we have such huge amount of data, and we use those data in order to make smarter decisions. And he mentions then, let's say, financial services. We know that in some sense all the predictive modeling for the stock behavior is in some sense ingrained in the financial service industry. In the insurance industry, we have death tables, so statisticians think about your rates for life insurance. And he mentions several industries. The funny thing is he doesn't mention IT, and he doesn't mention software engineering. And then you start wondering, why doesn't he mention IT and software engineering? Actually, we are good at processing data, but currently we don't use it at all. So let's see how he actually defines analytics. And I found this table in some sense quite neat. So he thinks about what's the data that we have, the data from the past that we can use for information, for reporting, the data in present that we can use for alerting, and we can also, in some sense, interpret the data and use it for insight, for recommendation and prediction. And so let's just take two examples, alerting. So when, in some sense, the stock markets go down because there's one stock that falls rapidly, then by now, in some sense, they close the stock market because of the disastrous effects that it can have. What does it actually mean for software engineering, right? Do we have actually an alerting mechanism that tells us that something bad will happen if we continue on this path? And we know that, right? For if we actually check in branches or work concurrently on branches, it would be great that I'm being informed that there's something else working on the same file. And if we want a later merge, it will lead to a merge conflict. If we want to ship software, I think it's super important that, for example, we ship software so that it hits the market at the right time. For Christmas, for example, Kinect. But can we actually say 6 months in advance whether we will be ready in time with our, in some sense, engineering? And what are the mitigating things that we should do? So I think we have, in some sense, this is a huge opportunity to have an impact on software engineering if we use analytics. So let me take that, make that more concrete. Yesterday you heard a lot about concurrent objects and concurrent programming. Actually, there is one concurrency going on a much larger scale. Is if we want to develop something like Windows, then obviously we have to split the work and have to do the work concurrently. We can't do it sequentially. And so in order to do that, the system that you use is actually a version control system. What you do is, in order to isolate the individual groups from changes that happen elsewhere, you use branches, and then, in some sense, they have to be merged later. So in some sense, what we do, in some sense, in the big scale to organize people and their work is very similar how we organize the software themselves. And of course, there are benefits and costs to everything. So the benefits is that you can actually work relatively easily if you're isolated from the churn that happens elsewhere. But there's a huge cost to it. Namely, you have to integrate your changes back in the tree, and while you're working locally, somebody else who might actually depend on your changes doesn't see them. So we use software version control systems since 20 years, I think every big company. And then you go to Google, I have friends in Google, and I ask them, so what version control system do you use, and how many branches? You say, and then you hear Google says, oh no, we think that branches are completely broken, we shouldn't use them at all. And then you talk to the engineers, and the engineers say, we really suffer under conflicts. You go to Microsoft, that's what I know best, and Microsoft says, we use branches in order to isolate the people. But then there are other people within Microsoft says, oh, and by the way, we really have a hard time to integrate all these branches back together. So we have two big companies that actually say something completely different, despite that we are a science. And so I think it's really time that we analyze it more systematically, what happens with our version control system, and how should we actually set up these systems so that they work optimally. And of course, we are scientists. We use some data. And so this is, for example, how worse can it be? So this is just one file within Microsoft. I don't tell you which one. And there are little colors here and little edges. And in some sense, it doesn't matter too much. It's in some sense the number of colors that count. And so the dark blue ones are actually edits. So there are probably 60 edits on this code. The turquoise bubbles are branches. So these 60 edits have to be propagated to 30 different branches. And by the way, the black bubbles are in some sense always undo operations because something didn't fail. And in order to do this whole process, we needed 200 integrations. That's all the yellow bubbles. So there is a huge process involved in running big organizations with version control systems. So we want to optimize it. And we want to use analytics to do so. So we want to build alerting systems, recommendation systems, and actually even refactoring systems. So how do we go after it? So this is the area of empirical software engineering, and they use in some sense two different means, qualitative and quantitative. Qualitative is we'll do surveys. We ask the people what's their perception, what goes on, and then we use quantitative data to see whether there's actually a match and how we can actually move forward. So let's do that. So we ask the people in Windows who do lots of integration, what are their main pain points? And since there's almost no literature, but there's actually one nice paper from 2008 in what's called Streamlines Branching Patterns for Parallel Software Development, and they mentioned 12 antipatterns. So antipatterns are things that you should not do. And so we asked them, how frequently does this antipattern occur in your experience, and how high is the impact? And they, I can probably mention 4 that came out. So Big Bang merge is when all the binaries are merged together at a single point in time. And that's obviously a bad idea because in some sense you get too much churn. Development freezes before we actually ship a product. We really want to make sure that we have a stable version. And so as a consequence, in some sense, all the work stops and people are really annoyed. And these are 2, in some sense, managerial decisions that we can't fix. But there are 2 other ones, integration wall and branch mania, which in some sense we can address. And so how did we go after them? So integration wall means that there is a misalignment of, in some sense, the branch structure and the work that people are doing, their goals, what they want to achieve, build a particular feature. And so here is how we go after it using quantitative means. So we said, okay, so let's take, in some sense, a cross product of all the different branches. So each 2 branch, and for each branch we check, we figure out what are files that are, in some sense, impacted, changed by this branch, and who does the change. So we take these 2 numbers. And now we take, in some sense, we look at each branch with each other. And then we say what we really want to see is that actually different people work on different branches. And so this is a heat map where on the x-axis is file similarity and on the y-axis is developer similarity. And then you figure out, so you really want, in some sense, most people and branches working in the in the lower left-hand corner. So most pairs of branches are not similar, and they're worked by different people. So if you want to merge something back together, it's just fine. If you actually go higher up and says there are the same set of people, but they work on different set of files in different branches, that's fine too, right? It's even fine if the same set of people work on the same set of files in different branches. But what is really bad is, in some sense, is the 4th quadrant, where we see that, in some sense, different team members work on the same files in different branches. And then, in some sense, it collapses. And now you can actually do something interesting over time. You can see is how did the organization change and how did the branch structure change. And you see, for example, from Windows Vista to Windows 7, there was an organizational change. And that led to the fact that there, in some sense, are more collisions for the source code control system in Windows 7 than there are in Vista. So not every organizational change is actually the best when it comes to organizing work for the individuals. So now we understand which are the branches that will be really bad. But we want to do one more thing, is actually we want to figure out which are the branches that we would best take out of the set of branches that exist already. And so now the question is, how can we do that? The good news is we can go back into the past. We can pretend that we would build Windows very differently by replaying the history. So what we actually do is we say, okay, let's go back into the history when we started, for example, Windows Vista or Windows 7, and rebuild it differently because we have all the check-ins that have happened over this period. And we take out a certain branch, and we see whether the velocity, so how quick a certain file was in some sense reached the main branch, how quick that actually changed. And we get in some sense to the following scenario, that you can really look into the data and you can model taking out certain branches, as we did here on the left-hand side. And we see that in some sense for certain branches, it really helps with code velocity, because in some sense, they are actually hampering the agility. And there are other branches which are actually quite good for conflict avoidance and that you don't want to touch. So in some sense, since we know in some sense the names of all the red dots, we can now go back to the organization and suggest this is the file, this is the branch that you should really kill. And then in some sense, your organization will have a more agile engineering part. So with this, I want to conclude. I think as what we see right now is that analytics for software engineering will have a big impact in the future. Whenever I tell the story within Microsoft, people are jumping up and down and asking, can we have this? Can we have this? Because it, just for the branch analysis alone, it leads to a better development structure, higher code velocity, efficient scheduling, and most likely to fewer bugs, because the merge conflicts will be fewer, and that's where actually many errors are being introduced. So this was one story, analytics. There's another story that goes on. And so let me step back a little bit and look into the hardware area. So in hardware, we typically deal with circuit designs. And people actually are using things like VHDL to describe their hardware and then generate netlist. But because of various reasons, they actually take the resulting netlist and fudge with it, so that it, in some sense, they change the generated code. But they don't want to change the semantics of the circuit. And so they actually then use equivalence checkers. They check that two circuit descriptions are actually the same. And so why is this a success story for formal methods? Because circuits are just Boolean formulas. And we have seen a rapid progress in solving Boolean formulas over the last 15 years. And so far that, in some sense, this becomes a standard tool. Nobody's thinking about it in hardware companies that they use equivalence checker that builds on top of formal methods. Why did it work? Because it's a simple problem. These are just Boolean formulas. There is no abstraction in digital circuits, as we have in procedures. There is no heap involved. There are no loops involved. There's no recursion involved. In some sense, that's a simpler problem than building an equivalence checker for software. But on the other hand, suppose that we would have an equivalence checker for software. It would be so cool because we do so many refactorings all the time, and we never know whether we actually change the semantics. So let's see how we can build an equivalence checker for software that really takes into account the heap, the globals, and recursion, and function calls, and what have you. So how do we do that? So here's an example, a very simple example, obviously, how we can encode, in some sense, equivalence of programs. So here are two swap functions. The first swap uses a temporary variable, and the second swap operation uses just addition and negation because we are swapping integers. And we know that they are the same. So how do we encode that they are the same? We generate formulas. We generate a formula from the first program. And so notice that in some sense, whenever there's an assignment to a variable, this variable gets a new name. So in this sense, all the variables are unique. In some sense, the updates are gone. And we do the same for the second one. And we name the resulting value that we assign to x and y, then swap1.x and swap2.x, for example. And then we only say is, okay, they better be the same. So we could say is, oh, let's make sure that swap1.x is equal to swap2.x. In fact, we do something slightly different. We actually add a negation of what we want to prove. Okay, so why is this? Why do we use this negation? Because we use a particular proving technology that's SAT solving, or actually satisfiability modular theory solving. And so if we actually then ask the theorem prover, does this formula hold with the negation? And it says it does not hold, then we know that the programs are the same. The beauty of this funny encoding is, if the programs are not the same, then the theorem prover will give us an assignment of values to variables, and that's exactly the trace under which these two programs are not the same. So that works pretty well. And so what you see is there are formal methods in the game, but ultimately we are doing equivalence checking. You haven't seen really a specification, because we use programs as specifications too. So there are lots of problems, as you can imagine, how to encode branches, loops, heap. But let me just show you one other thing. How do we encode procedure calls? So here are two functions, foo1 and foo2. And they both call out to bar. And as you know, bar in some sense get past z, but z is computed very differently. Namely, once with x plus y and one with y plus x. Obviously, only the semantics knows that they are the same, but on a syntactic level, they are very different. So, and we encode it by introducing another function that's called f_bar. So we could unfold the method there, and suppose now that we want to check equivalence of main, then we would unfold all the procedure calls. It would result in a huge formula, but we don't have to uncode all these procedure calls, because we interpret now a procedure call as an uninterpreted function, and that has a very nice effect, because for uninterpreted functions, we know that if the arguments are the same, the results will be the same. So the theorem prover deals in some sense with a symbolic representation of the procedure and not with the real code, and so as a consequence, the formulas stay really small, and we can still use our theorem prover technology. So we actually built a tool, and this tool looks almost like tools that you already use. That's a difference tool, right? There's diff in Unix, for example, or WinDiff on Windows, but they work syntactically. This one works semantically. And so it builds on verification technology. And the nice thing is, in some sense, it's actually really pluggable for different languages. So what does that mean? You can now check whether two versions that do something very differently in the way that they produce a result, that they are the same. So this is really the version and application compatibility problem. So do these two versions do the same thing? And it also helps with, in some sense, automating the conflict resolution for our branching. But you can also do it over different languages. You can ask, are the two programs that I have in IL and that I have compiled to x86 the same? It's still an equivalence check. And so this is actually known as translation validation. So there's one technique that really addresses both needs and is very practical. And people never write actually any specifications because we use programs as specifications. So how does it work? So there is in some sense this Simdiff tool that takes two inputs and produces in some sense then a nice result, whether things are the same or not. And in order to adapt it to different source language, there's just a pre-compiler available that takes either C or IL or ARM code or what have you. Okay, so let me show you a small demo how that works. So here are two just C code. A little evaluation of expression tree. And you see it looks very, very different. But if you look carefully enough, it actually should be the same, right? So one doesn't use macros. It doesn't use a switch. It doesn't use locals. It does everything in line. And the other does the things a little bit more structured. OK, so here's our Simdiff tool. And if we run this, It will hopefully tell us something. And it says, all matched procedures appear to be partially equivalent. So we are very vague in what this says. So they should better be equivalent. But you don't check, for example, whether the termination is exactly the same. So there might be problems in termination, or there might be problems in overflow behavior. We can turn on knobs that they can be checked as well. But let me maybe introduce a slight change here and then see what happens. Suppose that we accidentally use the wrong operator between the two different versions. And so let's run this again and see what happens. OK, so now we get a counter example, a trace. Let's look at this trace. And in some sense, let me first maybe point out. So here we have the operation. So what did we actually change? The operation 2, I think we changed. So here it assumes that operation is 2. And obviously here we see that let's see, the first operator is 1734. The second operator is 0. And as a consequence, the result here is 1734. Because we, else, is that right? Yeah, we do a negation, right? 1734 subtracted minus 0 is still 1734. But in the other case, our result, our result is, what's our result is 0. So I'll do it like this. Because in some sense, if we actually multiply them, they are 0. And so then they are different. And so now that there are, in some sense, concrete values in this trace, in some sense, we could make the output probably nicer. But we never executed this code. In some sense, it was all theorem-proving technology that, in some sense, gave us counterexample. And we reproduced it back into our code in order to figure out what's the difference between these two code versions. OK, so let me continue there. So what we have built and are currently building is lots of tools that are based, that in some sense take some existing program or existing technology like test case generation, and we make them semantic based by translating programs into formulas. And that really helps quite a bit and gives us new capabilities. So we have seen this for Simdiff that really checks for, in some sense, correctness of refactorings, for application compatibility for compiler translations. And in fact, you can even extend it so that it checks for refinements too. So many of these tools are available actually on the web for Rise for Fun. So go to this website and check it out. And with this, I want to conclude this part of the, in some sense, formal methods tools. And want to move a little bit on to future platforms. So what's going on? So 20 years ago, we had no internet. And today, every third person on the planet is connected to the internet. What does that mean actually for us? It means that, for example, the browser became a super important platform because that's how we typically view everything that's on the internet. And there's something else that we know is that people spend lots of time playing. Can we use those facts in order to excite them, in some sense, for computer science? And how do we do that? So we just learned about equivalence checking. And one of the fun things is we could do something as a game on the web, too. And so together with Tao, who visited us at some point in time, we came up with an idea to use our test case generation technology that uses theorem proving in the back to actually use it for playing games. So what's the game? So there's a hidden program that's given. And you as a student are supposed to write a new program. And then our technology checks whether they are the same. And then you win. And if they're not the same, we'll give you counterexamples. And so in this case, it's not verification technology that uses verification condition generation, but it uses a different technology called dynamic symbolic execution. But in some sense, it might not matter too much. So with this, I want to introduce you to Peli de Halle, who built the system together with Nikolai Tillman. And he will give us a short live demo of PEX on the web. And so if you are bold, you can actually load it in your browser and do the same thing as he did.
Is this on? Can you hear me now? OK, cool. Yeah, if you stop listening to us because you're playing, that's OK. It's called pegsforfun.com. It's online. You can go and play with it. And I'm going to switch to the browser. It's a web-based application. This is JavaScript and HTML. So it runs on all browsers. And I'm going to tell you a little story about this website. We've been developing Pegs for 5 years, and then we would go in conferences, try to show it, but there was always a problem about having people have this right environment to try it. So we got frustrated and decided to write a web-based interface for that. So what you see here is basically a text box where you can write C#, and then a big black button where you can run the tool. And that's what we started with. In fact, we started with something like this, just a text box where you can write C#, and when you run it, it basically tells you. So in this case, we have a method that takes an input, and then there's an output, and it's extremely boring in a sense. It tells you that, well, you always return what you've entered. And then what we will allow people is to use the PEX tool that explores your program and uses dynamic symbolic execution to generate interesting inputs. So for example, if you write more interesting programs like array accesses that would crash in some special scenario. And by the way, I'm going to talk about that later, but we also worked on giving a great experience to the user. So in this case, in order to hit the exception branch, so in order to go here, you need to do some more advanced analysis, and we used the PEX test generation tool. So in this case, so I change the program, and I have a compiler warning, so I'm just going to change it here. So it's an IDE-like experience in the browser, and that was really the goal when we built Pegs for Fun. And now you can see that you have more interesting behaviors that are happening in your program when you pass an empty array or not enough elements. And there's all kinds of things that are happening. And this is showing the test generation engine that Pegs is. And we deployed that, and we saw that people came in, tried the samples, and never come back. They basically say, oh, this is great, but it's also boring. And TouchStudio suggested to us to turn that into a game. So instead of just having to explore a program, we want people to actually change the programs. And what WordForm said is basically the following. So we have two programs. So the user has to write a program. Let's say in this case, he always returns 0. And then we have a secret program. That is the specification that does something. In this case, we're going to return -x. And now what our tool does, it's going to check that they're both the same, right? Now, if they're not the same, we report an error to the user. And I guess something is wrong. And this is all in the browser, running in Redmond. And you can see that now we start to have a more interesting experience where we're telling the user, look, you need to go and figure out the specification, and you're wrong for some cases. So when I is equals to 1, it's incorrect. Now, the feedback right now is not good because you don't really know what the secret implementation does. So we took that and turned it into a real gaming experience in the website. So that's what I'm going to show you in this other page. Whoops. In fact, you're seeing the solution here. OK, let's reboot that. So this is what players see in Pegs for Fun. They have their startup method and usually a pretty cryptic description of the problem. In a sense, go and figure it out because it's a game. So we don't want to give away the solution. And they start asking questions to Pegs. So they start asking whether their program matches the secret implementation. And we give them inputs and outputs. So we map X, and we tell them that for some cases, like when X is 1, the secret implementation returns -1, and you return 0. You're wrong. You need to fix that. So if you play a game, the first thing you try to do usually is to cheat by definition. So one way of cheating all those competition games is to actually build a huge if table and just try to beat it by brute force. Now, you can't do that with PEX because each time you add a branch, we generate a new test case for it. So it's much harder to beat than other game engine. And as you can see, we fixed those two cases, but there's still a new one that's wrong. So at some point, you need to kick in the brains and start thinking and abstractly. So we've seen a lot of solution to this one. I don't know if you have a hint about how to solve that problem. I think the most funny one that we've seen was x minus 2x as a solution. And in a sense, it's OK. Not the best code ever, but you still get the warm U1 feeling. Now, you might be wondering, this is a bit silly. Minus x is probably easy. So one of the other challenges that we have, and here you can see that, for example, this challenge has been solved 3,500 times, and they've been solved quite a number of times. Challenge factorial, for example, is another challenge where the student has to reverse engineer factorial. And we really don't give him any hint. We just tell him, look, just go and figure it out. And people spend hours solving that. We see in the logs people doing 50, 60, 70 attempts and minutes between every attempt. They probably fill entire tables of numbers on the side and things like that. They really get hooked up. And you can see that when you look at the live feed. So this is a Twitter-like feed of the live activity on the website. And you can see that you have people playing right now at this extremely geeky game. But in a sense, this is the puzzle. This is the ultimate puzzle. If you're into puzzle gaming, it doesn't get any better. And I guess it's Thursday already, so people are already slacking off at the office and playing PEX for fun. And with that, I'm finishing the demo.
Yeah, thanks a lot. So. So we have PEX for fun now probably 9 months, and as you have seen, there are probably more than 110,000 people in some sense playing puzzles, and there are 500,000 that have been solved so far, or 450. So let's see, just reflect on it a second. So, oops, one thing. So what we really took is a programming experience into the cloud. We in some sense, try to understand how do people learn? What are they excited about? And then we came up with coding dolls. And what we also saw, it's super important if people want to do coding dolls, that they actually start socializing. So having the live feed and in some sense a champion list is really important. And then people asked us, oh, actually we can use that maybe for teaching an automatic grading, because we know in some sense when things are passed. And we can also turn it around. So suddenly we are in the, we have 450,000 programs in our database, and you can start mining them. When people don't find the right solution, what is actually the reason that they can't solve it? Is the specification too weak, or do they have problems to express certain concepts? And maybe it would be a great way to see is whether we can improve our Visual Studio, Eclipse learning experience by learning from why people fail solving certain programming tasks. So there's a lot of research, and I would encourage the audience maybe to reach out to us and see is whether somebody wants to work on this area. There's something else. And I think the web has really changed the field. But right now we are in another revolution again. And that's actually that the smartphones change the field again. So there are quotes that say, fiscal, third quarter 2010, smartphones outsold PCs. Not sure whether that's true, but it's definitely true for this year. That means there are more smartphones, more computers being sold than laptops, so smartphones, than laptops, PCs, netbooks, and so on. And furthermore, you also have to recognize that for many people, a smartphone will probably, in particular in developing countries, the only computing device that they will have, right? We can afford to have 3 computers. They can't. And today's smartphones are as powerful as PCs from 2000. Actually, many of our smartphones have already dual core. They're probably even more powerful than 2000. But they can't be programmed. And so in some sense, I think it's really a limiting factor because people are really creative in what they want to do. And it's great to have 300,000 apps here and 200,000 there. But there are, in some sense, billions of people, and they need, in some sense, something special. And there's really the long tail. They want to personalize the experience on the phone. So if this is a computer and we are, in some sense, the software engineers, why don't we enable them write programs on the phone? And so with this, I want to introduce TouchStudio, which was developed by Nikolai, Peli, and Mihao. And maybe before we go into the demo, let me add two things. So what we want is actually address a different audience. We want to see is if let's say my daughter is on the phone almost all the time, playing, socializing, and actually she would even like to program. And so I think if we want to generate excitement for the next generation, we should see is what do they want and where are they excited? So this is in some sense programming on the phone is not for the professionals. They will have their laptop on a big screen. This is in some sense for everybody else, like me and you and my daughter. So what's going on? It's actually lots of challenges. If you just think about that you only have a phone, how do you do editing, authoring, debugging? The good news is the phone is always connected to the cloud. But what programming model do we actually use in order to simplify the programming to the cloud? The next one is social aspects. People want to share, exactly like in the game experience. They want to share their programs. But as soon as you start sharing programs, oh, you open a box of Pandora because you have all the security and privacy issues involved. So there's lots of fun research to do over here. And without further ado, let me introduce you to Nikolai, who will give you a demo with TouchStudio.
Can you hear me now? Yes. Okay. So I'm going to show you a brief overview of TouchStudio. So the basic idea is that's a programming environment on the phone. You don't need any other computer because, as Wolfram said, that might be the only computer you have. If you ever tried to program a mobile device before, you might have noticed that you normally need a normal PC or laptop, which is really your development platform. And it's quite a challenge to take such a small device and turn it into a relatively productive programming environment. So you can install TouchStudio on your own Windows phones. It's on the marketplace. So let me get started. At the top level, there's basically a project system. You can have different projects. Let me pick one of them, which is very popular. It's an application that basically allows you to customize searches to your song library. So by default, what it's doing here is it's looking for all of your songs and picks those which have at least a duration, or which have at most a duration of 180 seconds. Now I can simply run it by pressing the run button. And it will now post all of the results to what we call the execution vault. It's basically a log, the output of the program. And I could pick a song here now and play it. So, can connect it. But maybe, I guess you can hear it. Okay, let me stop that. So that's great. People love that. We can now customize it. Let's say you don't just want all the songs that are short, but maybe you want to look for a particular substring. So now I can go in and edit the code. And what we did here is we created a user interface that basically allows you to do everything with the touch of one finger, which is pretty challenging. So navigating through text is extremely difficult on these small devices. So it's important to have a user interface that is customized for the finger. So I could say, I want all the songs that are short, and I want songs whose name, so you're seeing, I'm now in an expression editor where I have quick access to all the properties that are relevant. So I can take the name of the song and what's available on strings. Let's say when I do my search, I'm not interested in lowercase, uppercase, so I take the string and turn it to lowercase, and then I can call a contains function. And you see that the number of tabs I'm doing, it's quite similar to what you would have to type in a normal editor. So our language is a typed language, not for the sake of being type safe, but in order to provide IntelliSense auto-completion feedback for the user. Okay, now comes the most difficult part, typing text. Let's say I want songs that have the word dig in it. Okay. And go back. So now I've customized my search, and I can run this modified program, which will now give me less songs, exactly one. I could play it again. So you might know this problem. Your phone is playing some sound, it's ringing. You're going to a meeting, and you want to turn it off easily, right? I don't know if you have seen the Windows Phone. It has like 5 buttons around it. Which button should I press now to turn it off? So what I can do now is I can customize the experience how to turn off songs. So I can add a new statement. Very easy. What I'm going to do here is to implement a little event handler loop explicitly. So I'm going to write a loop that runs forever. And then I'm going to add event handling code in it, which will be executed periodically. And what I want to do here is I want to check if the phone, whether I turn it over. So the phone has a sensor to measure acceleration. In particular, it measures gravitation. So if I take, if I access the sensors of my phone, including the accelerometer, and so I tried out this demo while I was walking here, so on the go I was programming. I figured out I have to look at the z coordinate. So it has 3 dimensions in which it can be oriented or being accelerated. And when that exceeds a certain threshold, and I figured out that 0.7 is a good value, then I want to basically just turn off whatever is currently playing. So I can go to the player and say, stop. So let's try that. And I should do a little bit more. So this loop will now run forever. And I only really want to do this check once in a while. So I can add a little sleep statement. So this is the first version of TouchStudio that we have shipped just this Saturday. And in the next version, we are planning to have a better event handling scheme. But this is how it works right now. So I can go into the phone and say, sleep for a moment here. Let's say for 1 second. Okay, so now run this program, I get my song, I can play it. Let me turn up the volume. Okay, it's playing. Then you go to your meeting, or your boss comes in. Off. So, to show just one more thing, we could also make it even more interesting. So right now I'm completely stopping the song. So what if the meeting is over? So I can go in and refine it a bit, and I can say, just pause it. And then I'm going to add another if statement, saying that when I access the acceleration information of the phone, and now I go below a certain threshold, which is minus 0.7. Then I want to go to my player, and I want to resume. So I don't know if you could have written this code quicker in a normal editor. Let's try it out. So I pick my song. It takes a moment to build up. Okay, meeting starts. Meeting is over.
Good, wonderful.
Meeting is over.
I think there's in some sense so much excitement in this area where you can really combine the mobile experience with the cloud, for example, producing maps and pathways. It's really straight line code, but since we are running a little bit short on time, I'll leave you with this. So in some sense, yeah, accessing maps and locations and is a joy. But there are lots of research challenges open, and this is a research group. So we don't know what's the best way to share, in some sense, code, security, privacy. I mentioned that earlier. Power is, I think, a really big one, right? So what's the best way that we can program those devices that they use as few power as possible, because we don't want to hear the song only for a short time and then the battery is gone. So I would suggest download the app. It's on the Windows Phone App Store, and you have a Windows Phone. And let us know what you think. And there are lots of people twittering about it. So it's really fun. It's taking off. And actually, my daughter wrote her first program on the phone as well. So that was really nice. Okay, so I told you about 3 stories that I think are really making an impact in the next 5 years. I don't know what will happen in 20 years out, but I think we will see much more analytics for software engineering in order to make smarter decisions for engineering. I think we will see many, many more tools that build on very solid logical foundations, except that you don't see that in some sense there's a theorem prover behind some of those things. I think we should really move on, get over from the PDP-11 and laptops and move over to the cloud, the data center, to mobile devices, and actually also games. Let me just make one comment here. I think the prediction for games, it's a 50 billion market in 2015, and it's all software. And there's very little software engineering right now in it. So I think it's a great opportunity for this community to have a big impact. With this, I want to conclude. As you know, I'm only a manager. I'm really blessed with a great team. So these are, in some sense, this is my team, and there are lots of websites where you can check out the stuff that we are doing. Thanks a lot. Yeah, I'm happy to take questions, please. Bertrand? Oh, is there? There's. Maybe I can shout. Yeah, and I'll repeat the question. Yeah. Oh. Actually, you're hearing. Just a kind of strategic question. Do you really think that phones are going to displace laptops? Because it seems to me that for today, if you have a phone, you also need a laptop anyway. Yeah. No, I don't think that, let's say, in all the industrialized countries, I don't think that will happen. In some sense, let's see. So even Apple intentionally doesn't put the iTunes, makes it iTunes available on the iPad, because otherwise there won't be no need to buy a laptop anymore. So I think even other companies recognize that they really want to keep the laptop alive, and I want to keep my laptop. Let's go to India and China, in some sense in markets where this is not as wealthy as ours. So the question is, what will happen there? They have already the phones. Today, in some sense, a relatively cheap phone, but they are looking for the next kind of phones. And so do we want to give them the opportunity to, in some sense, personalize their experience on the phone if they don't have a laptop? And so that's an interesting question. It's about the future. We don't know how the future will play out. But I think we should consider that that is a trend that might happen. Wait, I'm wondering why you're mainly speaking about programming when you are saying that you give a title future of software. OK, so the group is called Research in Software Engineering, but actually a large part of what we do is actually programming languages. And ultimately, all our ideas are communicated in some form of language, and that's why I think languages are important. I talked about equivalence checkers. That's a software engineering tool. But in the end, it's also, in some sense, needs the notion, what's the semantics of the language? So in some sense, I think if we want to deal with programming artifacts and not only with processes, we'll come to something that's can be widely called programming language. And so that's why I think it's important that we care about those things as well. Coming back, for example, to the empirical software engineering community, it's unclear. There is lots of claims which programming language is actually more productive, and there are very few research results that can prove that one is really better than the other. Nevertheless, we have a strong belief that one is better than the other. So I think there is, in some sense, we are, as software engineers, often bound to our languages that we are using. So it's an important topic for us.
I did not understand what you learned from Google and the branching. Can you explain this a little bit more?
So what I only wanted to say is there are different companies that have very different opinions how to set up branch structure. And, and we are using version control systems since 20 years. And there are two different companies that say this works for us best and this works for us best. And it's not the same. And so why is it that it works for them better and doesn't work for Microsoft, or the other way around? I think it's a wonderful question to ask, because we change, in Microsoft, in some sense, branch structure from version to version to version. And typically with a gut feeling, we think this is better because our organization changed or the architecture has changed. But we don't have, in some sense, evidence that that is correct. So what I wanted to point out is, man, as a community, we seem not to understand what we are doing. And it's time that we clean this up. Okay. Yeah.
And then you show us these very nice little examples.
Yeah.
What is the connection between the two?
Okay, so little examples. The technology for PEX is based on dynamic symbolic execution. There is a tool that's not called PEX, but SAGE, that uses dynamic symbolic execution. And that is being used in order to test all file parsers. It has been used to test millions of lines of code in Windows 7, and there's a whole team in Windows 7. Windows 7 was 4 people. Because of its success in Windows 8, it has grown quite a bit. That in some sense uses exactly the technology in order to find bugs, access violation bugs. And so the good news is that technology is so successful that there were only 5 bugs that we know of that have been reported to us in millions of lines of code after we shipped it 18 months ago. And that was tested automatically with SAGE. So it's not functional correctness. It's only no access violation, no buffer overruns or whatever. But I think it's working pretty well. So I can only show the little examples here because we don't have a data center. But it should give you the gist of where things are going.
Right, well, I think we must stop there and take some of the questions afterwards. Of course, at the Demo Fest, both Wolfram and his team will be there. And I'd like to thank you, Wolfram, for a most inspiring talk.
Wonderful. Thanks a lot.